Okay, so our last talk for this morning session is going to be given by Fyodorov, and he's going to tell us about beta-Hermite ensembles and some recent results. And this connects directly with interests of Freeman Dyson. So this is very much a part of the conference where we wanted to celebrate Dyson's contributions, and I think Jan is going to do that. Jan.
Thank you, John, and I'd like to thank all organizers for an opportunity to attend this very nice conference, bringing two communities, RMT communities and number theory communities together. Interestingly, we already have seen a few examples how ideas which appeared in the context of various sub-areas of theoretical physics eventually, after sometimes 40, 30 and more years, have some relevance and I would say repercussion in the context of number theory. And indeed, we are here to celebrate this meaningful and very important encounter between Montgomery and Dyson, who paved the way. And I wanted, in this context, just to start with, sorry, I need to adjust to this. To start with, maybe describing in a little bit more detail fundamental contribution which Freeman Dyson did in early 60s to the field, basically, which paved the way for describing complex systems of many interacting particles. And in that time, it was not appreciated even a single particle in a special environment, which we call the field of quantum chaos now. And basically, this was done in a series of 5 papers, which under the common title Statistical Theory of the Energy Levels of Complex Systems, all published in '62 in Journal of Mathematical Physics. And in those papers, basically, Dyson start with classifying self-adjoint, or we can say just synonymously Hermitian Hamiltonians of quantum systems. He has in mind particular physical systems responsible for scattering in or for properties of complex nuclei. Therefore, he thinks about constituents like neutrons or something of this sort, which in particular have can be described as having a special quantum property or quantum characteristics called spin, or in particular half integer spin, like so-called fermions, in particular electrons and neutrons. And he thinks how one, in very general terms, should classify by symmetries these Hamiltonians if we know very little of them, and what types of random matrices we should use to hopefully faithfully describe their properties. So we realized, I mean, a very big majority of systems, or in fact, overwhelming majority of physical systems, they are invariant under a reversal of time. And if these systems also do not have any spinful particles, or they have an even number of half integer particles with half integer spins, then Dyson realized that such systems should be described, or can be described by Hamiltonians, which can be thought to be represented, if in finite dimensional Hilbert space, for example, by just invariant with respect to transposition. So in terms of matrices, this would be symmetric matrices, and since they should be self-adjoint, I will explain later on why in quantum mechanics it's natural to think of it's meaningful to speak about self-adjoint Hamiltonians. then this will be basically corresponding to real symmetric matrices. Or if one discusses not Hamiltonians, but the corresponding evolution operators, which are given by exponential of minus imaginary unity time parameter times h, then these unitary matrices will be unitary symmetric matrices. The corresponding random matrix ensembles, if we restrict ourselves to Gaussian measures, are known as Gaussian orthogonal ensemble for Hamiltonians, or circular orthogonal ensemble for unitary U's, which can be represented as U transpose U and U taken uniformly from Haar measure. These ensembles are labeled with index beta equal Dyson index nowadays, beta equal 1. And if it sounds mysterious what this index stands for, it will be clear. Meaning of this index and this labeling will be clear on the next slide. Now, there are also physical systems, especially those in strong magnetic fields, in which system is not any longer invariant with respect to reversal of time. And these systems should be characterized by general unitary evolution operator and by just Hermitian, complex Hermitian matrices. And corresponding random matrix ensembles are known as Gaussian unitary or GUE ensemble for Hamiltonians, and circular unitary ensembles for unitary matrices, just uniformly distributed with Haar's measure, and they are labeled by Dyson index 2. And finally, systems which are time reversal invariant but contain odd number of half integer spin particles should be described by, in fact, matrices which have additional structures imposed on them. In fact, it's useful to think of them as being of even dimension, so not n by 2n, and having special structure, which I do not give explicit description here, but it is called quaternion self-dual, and the corresponding evolution operators, they known as being on belonging to circular symplectic ensemble, because this quaternion structure induces additional symmetry related to symplectic groups, and it's labeled by beta equal 4. This classification is known as Dyson threefold way. We've heard yesterday that, in fact, and I should stress that, in fact, this classification remains valid up to this day, despite the fact that we now know that there can be additional physical symmetries close to special points in the spectrum. So if we consider just a generic point in the bulk, this classification is suffices. But if one considers additional physical symmetries which may impose special properties close to some singular, in some sense, points in the spectrum, then one needs to further extend this symmetry to so-called 10 Alkland-Zimbauer classes or 10 Cartan classes in symmetric spaces. We've heard a little bit about that in Peter Sarnak talk yesterday. But for generic point in the bulk, this is still valid classification. Just to mention, because it will be relevant later on, I'd like to remind, or maybe some people here not that much exposed to quantum mechanics may just not know why Hamiltonians should be considered meaningfully, in the, at least for the first glance, as self-adjoint or Hermitian. This is related to property, basically, to have the corresponding evolution operator unitary, which is basically the same, and unitarity is necessary in order to evolve quantum mechanical eigenfunction, or better to say wave function, typical eigenstate in the Hilbert space, in such a way that it preserves its norm. And this normalization or preservation of norm is a physical requirement of, basically in the simplest case, if one just deals with a single particle, it's a requirement of conservation of the number of particles. That the particle cannot just disappear. If it was a single particle, then total probability to find it somewhere should be 1. I just ask you to keep this in mind, because I will speak later on non-self-adjoint matrices, and I will give some motivation. There is, in fact, motivation to study it. And you may guess that this will be for systems which do not, in fact, in some sense, in certain sense, preserve the number of particles. But so far, so good. We are dealing with self-adjoint matrices or operators. So they have all eigenvalues real, and Dyson was able to show that the joint probability density of these real eigenvalues for Gaussian ensembles in all 3 cases of this parameter beta equal 1, 2, or 4, or for all these 3 classes, can be written uniformly in the following way, where the most, okay, this factor is specific for the Gaussian measure that we use, but this factor, which is basically the Vandermonde determinant, modulus of Vandermonde determinant raised to power beta, and beta is exactly this Dyson parameter 1, 2, or 4 for time being. Basically, this factor is the most important and responsible for majority of correlation properties of eigenvalues in the bar. Its counterpart for unitary matrices does not have this confining or potential term in the exponential or wave term. It's just a uniform distribution of on Haar measure with in these 3 cases implies that the corresponding joint probability density of angles, unitary matrices are unimodular, so all eigenvalues are unimodular, they are on the unit circle, so it's natural to characterize them in terms of these angles or phases, and joint probability density of phases is given by very similar factor where lambdas are replaced by these figures. Of course, to have well-defined probability measures, one needs also to specify normalization factors, which in this context frequently referred to as partition functions. And indeed, the name is not just, I mean, it's meaningful because as Dyson noticed, if we just exponentiate these products, then one can write it down in the form which is basically reminiscent or just equivalent to thinking of particles living, say, in this case, on the circle, and basically it's model bona fide statistical mechanics model. Not unlike models considered yesterday in Tom Spencer's talk, is just different degrees of freedom, but still they interact, they logarithmically interact, and this weight basically is not, can be interpreted with parameter beta here, can be interpreted as Gibbs-Boltzmann measure on this space of configuration space of these n particles. And this analogy was very fruitful as Dyson used it, in fact implemented in many calculations. And these models of this type are now conventionally called in the literature Dyson-Coulomb gases. Coulomb, because this logarithmic interaction in 2 dimensions is typical for Coulomb interaction between charged particles. So one can think of these one-dimensional Coulomb gases as just being some projections from two-dimensional space. So in Dyson own words, I just in one of these 5 papers, he just writes that energy levels, which he associates with eigenvalues of Hamiltonians, do indeed behave exactly, and they will like charges repelling each other with the force very inversely with first power of the distance. Force is basically derivative of this potential, so it will be inversely proportional. And it has consequences in that thermodynamic notion of entropy, specific heat, and other physical notions can be transferred from the Coulomb gas to the eigenvalue series, proves very useful, gives us precise and well understood language to study statistical properties of eigenvalue series. And in fact, this idea that these are interacting particles and the interaction makes them correlated forced Dyson to introduce these important objects, that two-point correlation function that and in fact he was able to calculate them in all 3 cases, as I will show in the next slide, and which was very important in this in the case of discussion about Riemann zeros. So here I'd like to mention an interesting fact, that in fact Dyson was not able to calculate exactly these normalization factors, but he guessed them from particular cases, and he guessed them. They are given by such an expression, for example, for unitary case, and there is similar, slightly more involved expression involving gamma functions for Gaussian case. And nowadays we know that this is in fact nothing else. These factors, of course, can be obtained by evaluating integral over all lambdas or all thetas and requiring correct normalization. The resulting integrals, multivariate integrals, are nothing else. One can recognize them as special forms of Zelberg integrals. Dyson formulated them as a conjecture. They were not immediately, but in a few months, proved by in 2 dependent ways by Kenneth Wilson, a future Nobel Prize winner in physics for theory of phase transitions, and I think by Morris independently. But then I understand that, in fact, some interaction with Zelberg showed that even in year 1944, this fundamental integral was calculated, and in principle could be used to prove these particular guesses. So all this is an interesting story. And again, let me remind you that I think it is quite clear if you read those papers that idea to study pairwise correlations came from this picture of interacting charges, because it was standard way of characterizing behavior of plasma, for example, plasma of interacting charges. So basically, people use what is known as cluster functions. In case of unitary ensembles, one can define these cluster functions. Okay, Dyson introduced an important scale in the spectrum. He recognized that important scale is related with the main separation between neighboring charges or eigenvalues, which for unitary ensembles is just obviously will be circumference of the circle divided by the number of charges. So typical separation will be 2 pi over n. So if one defines this cluster function, which tells us about pairwise correlation between positions of these charges, where expectation is with respect to this measure, Dyson Coulomb gas, then he was able to evaluate in closed form using the method which he attributes to Mehta and Godin. But interestingly, Mehta and Godin considered different quantity. They did not, they were not led by this analogy with Coulomb gas, and they were considering more complicated object, which eventually they were able also to evaluate the distribution of distances between between neighboring particles. This is much, in principle, much harder object in the sense that it involves information about all correlation functions. So to single out pair correlation function, then higher order correlation function, I think it was conceptually important. But method, Dyson adjusted the method to these objects and was able to find these famous formulas. In particular, for beta equal 2, he found that the limit n to infinity, this correlation function takes a finite limit, which is now we call Dyson kernel. It's just sine pi omega, where omega is separation between 2 points measured in the units of mean eigenvalue spacing. So sine divided by its argument squared. This is for beta equal 2, and this is, I believe, the formula that basically he immediately recognized in Human-Gomory formula for pair correlations. But if you read original 62 Dyson paper, he says this is the least interesting and probably never realizable physically case. So let us do it. It's so simple that we cannot just resist giving explicit formulas for it, but probably it's irrelevant. Fortunately, it proved to be not the case even in the field of quantum chaos, and especially not so in the field of in number theory applications. But I think that Dyson really appreciated that he was able to calculate the same object for beta equal 1 and beta equal 4 explicitly, and in fact it's always expressed in terms of the same combination. It's just more complicated representations. So these formulas turned out to be universal, which is very important. This is exactly what we call nowadays Wigner-Dyson universality, that if one takes, in fact, quite different systems, but sharing these global symmetries, then we believe that in the local regime, and local regime is the regime when separation in the spectrum is comparable with mean spacing between eigenvalues, then this type of correlation functions and higher correlation functions will be in fact always given in appropriate limit by these formulas. Interestingly, although Dyson himself really presented it in this form with general beta, and moreover considered in some calculation beta completely arbitrary and used it as a notion of a temperature, obviously there was for many years people were not able to produce a well-defined bona fide random matrix which would have the joint probability density of eigenvalues exactly like given by Dyson Coulomb gas for beta which are not 1, 2, and 4. And this was even considered in some, at least in some communities, as a dogma that beta can be only 1, 2, and 4. So very interesting and I believe personally a very influential development happened exactly 40 years after the fundamental works of these Dyson works, where Dmitry and Nedelman, developing earlier ideas by Trotter, in fact were able to explicitly construct a random matrix, really a matrix of size n by n with random entries, whose joint probability density of eigenvalues exactly coincides with Dyson Coulomb gas for any value of positive beta. So construction is in fact very elegant. These matrices are not full random matrices, in contrast to the case of 1, 2, and 4, these Gaussian ensembles, where basically these ensembles in every realization are all entries are non-zero. Here they're very special. They're 3 diagonal. On the diagonal, one has independent Gaussian distributed just normal numbers. So all diagonal entries have the same distribution, so IID numbers. But off diagonal entries, they are not IID. They're independent, but their not variance, but basically probability density depends on their position along the diagonal. So they are given by the so-called chi-square distribution with so explicitly I just write in there. They are positive. They are all positive. The sign is fixed, but they are also distributed according to this distribution. So when one changes this k, index k, also one changes really the distribution. And then calculation shows that eigenvalues of these real symmetric matrices, so all real, will be exactly given by this with correct normalization factor. Similar construction, but with 5 diagonal matrices exists for unitary case. So one can construct. It was done just a couple of years after Dmitry and Dedena. I do not have a reference here. I think it was done by Kilip and Nensio, who constructed, provided similar construction. And this construction was, by the way, I think that construction was instrumental for proof of Najnudel and collaborators of some of the results on multiplicative chaos, which appeared already in this conference. So there is, in fact, intimate relation with what I start to discuss with the subject of this conference, although this is not exactly my goal to pursue it further. Okay, so what do we know about now in 20 years of playing with these ensembles? What do we know for properties of these spectral properties of these ensembles for general beta? So normalization that I used in the definition of the previous slide ensures that large n limit of the mean eigenvalue density, which is just expected value of the counting function, basic or empirical measure, better to say, but of empirical measure, counting function will be integrated empirical measure. So it's just a standard Wigner semicircle law for all beta independent of beta and supported in interval between -2 and 2. Interestingly, there was a quite explicit on one hand, but not very, I would say, user-friendly characterization of the corresponding limiting spectrum when n tends to infinity in terms of so-called sine beta process related to some self-adjoint random differential operator due to Falco and Virac, which gave boost to quite vigorous activity in understanding various correlation functions and distribution of that. And as we all know, or many people know in this audience, especially in applications to in number theory, characteristic polynomials play a central role. So I just give you, to some extent, they were attempt to study them on the local scales. And Falco and Virac a couple of years ago introduced the notion of stochastic zeta function, which is basically some scaling limit of characteristic polynomial looked at appropriate scale, and which reflects universal properties of characteristic polynomial on a local scale. Characteristic, although quite explicit, but if one likes to know some properties like moments, like two-point correlation functions, not that much is known. In fact, moments are known due to Higden-Snaith's old work for all beta. Yes?
It was work of Haldane and his student for beta, a rational number, which conjectured that the correlation would be a p times q dimensional integral. Do you know the status of it?
Yes, okay. Yes, indeed. There are some particular results. Indeed. Thank you, Peter, for.
Is that actually proven?
I know that some, not in full generality as far as I know. In fact, I think about correlation functions of characteristic polynomials. There are few nice results proved by Forrester, Keating, and especially an interesting paper by Desrosiers and Liu relating them to hypergeometric function of matrix argument. John may correct me if not exactly this, but I think it's in fact it's quite explicit. But if we try to really work out some user-friendly formulas, it's still, I would say, quite far in general case. One can extract some, for example, for negative moments, some singularities behavior, but to get explicit functions, we are still quite far from there. And I'm interested in that, and I just wanted to mention explicit result, which I was able to find in the literature. In fact, it was hidden already in the work of Aramoto on complex generalization of Zelberg integral long ago, and rediscovered by Su about 10 years ago. And this is up to appropriate normalization, expectation of the product of two shifted values of characteristic polynomial for this type of ensemble is given by basically proportional to Bessel function whose index depends on parameter beta. In particular, yesterday in Tom's talk, he mentioned result of Tanya Sherbina for banded case, which corresponded, in fact, for beta equal 2, where this will be then 4 minus 2, so will be 1/2. So Bessel functions 1/2, they are related with sign divided by its argument, and this is exactly the formula that appears. But this is a generalization. It was proved rigorously for beta smaller than 4 and conjectured to be valid for all betas. Technique did not allow to prove it beyond 4, but conjecture is. But this is the only rigorously proven explicit result which I was found, and which I will refer to maybe later on. So far, so good. We discussed these nice ensembles, and now I'd like to make a twist, which probably in this audience will be this conference will be considered as quite strange. Really, I would like to consider from this point as some deformation of these three diagonal matrices, which make eigenvalues of the corresponding deformation complex. So I will consider non-self-adjoint or non-Hermitian deformations of this ensemble. So why so? As I already mentioned in the beginning, self-adjointness of Hamiltonians, it must, if we deal with systems, for example, confined to a finite portion of space, and therefore conserving normalization and having discrete quantization of their lengths. But now imagine we deal with such a system, which we just, I tried to sketch here as a billiard. Some domain on which we study, say, Laplace operator. If we are especially vicious and like to say follow what Tom discussed yesterday, we can also introduce some random scatterers here to make life even worse. But anyway, this is a chaotic system, and if we consider it per se in a finite volume, then there is a quantization of eigenvalues of Schrödinger or just Laplace operator with given boundary conditions, say Dirichlet or other conditions making it self-adjoint, and corresponding random matrix ensembles will be for high excited levels will be adequately described by say GOE or GUE, depending on presence or absence of magnetic. But now let us physicists like to study such systems in the following way. They attach a large, what one can call a waveguide, and just send a wave or a particle, quantized particle, I mean quantum particle, which is a wave, from infinity, and allow it enter this domain, being scattered and then reflected back to infinity. Obviously, if we restrict ourselves to this particular part, there is no particle conservation any longer, because particle from this particular domain, probability to be found here will be always in any moment of time smaller than 1, because part of it comes from infinity and escapes to infinity. So should we immediately discard random matrix theory for description of this interesting process, or what physicists call scattering? In no way. In fact, it turns out that these systems can be, in fact, it can be derived from first principle that one can describe this escape to infinity by non-Hermitian Hamiltonians, where Hermitian part is just get deformed by a positive, by I imaginary unity multiplied by some matrix or operator which has only positive or zero eigenvalues, and this operator basically depends on the way we impose this boundary condition and the point of contact of this. It's just to keep in mind motivation. So in physics, it's perfectly legitimate and even important to consider non-self-adjoint operators. So motivated by that, I'd like to consider now non-self-adjoint deformation of these three diagonal ensembles, and really the simplest possible deformation, rank 1 deformation, characterized. So let us take in this basis just a vector, just first coordinate vector 1 in first entry and then 0 otherwise, and build basically a matrix which only has entry gamma in its left top entry, and multiply it with I as it's required by what I said about scattering. And let us consider now this object. First challenge is to understand, is it possible to say something about complex eigenvalues of this? Important thing which one can show separately, that in fact this introduction of this parameter gamma, any positive, any different from 0, immediately induces with probability 1 all eigenvalues to leave the real axis and move to the complex plane. Now the question arises, what is the typical distance to which they move in the complex plane? It turns out, this one can prove, that typical distance will be comparable with their separation along the real axis before this perturbation is imposed. So this delta. So there will be just a little bit randomly moving to lower complex plane. In principle, they can be everywhere, but typically they are at the distance of order of delta from the real x, or the imaginary part is negative and of this order. Now, interesting question arises whether one can calculate the joint probability density, Dyson-type Coulomb gas analogy for this deformed ensemble. This was done by Rostislav Kozhan a few years ago, who indeed found that one can write explicitly the joint probability density in this case. And let us discuss its basically its ingredients. Okay, apart from Gaussian weight, we have the following three ingredients. The first one is just a simple generalization of squared van der Monde determinant in the complex plane. This is our familiar van der Monde squared. Next term is, in fact, it describes interaction between position of eigenvalue in the complex plane and its image, its complex conjugate, and it's controlled by power depending on parameter beta in this three diagonal business. So if beta happen to be 2, so this corresponds to classical value beta equal 2, then this term is absent, and we are dealing just with squared van der Monde in the complex plane, and the last bit is the delta functional constraint, which is a simple constraint and must be present because it's easy to see that such type of perturbation must leave invariant basically or impose as a constraint that sum of imaginary parts of Z should be exactly equal to parameter gamma. It's very easy to see. And therefore, this is a well-defined distribution, and we are interested in telling something about correlations in the complex plane, or we may be interested in telling about this of these Z's. Unfortunately, all standard methods of random, going back to Dyson method, Kozhan, this orthogonal polynomial yet are not developed here. So apart from the case beta equal 2. For beta equal 2, about 20 years ago with Boris Horozhenko, we were able to solve this type of problem with orthogonal polynomials in complex plane. It's not a big deal. This constraint is important to have in mind, but it can be effectively dealt with. But for any beta, which is not 2, up to last year, there was no any progress and no understanding, even no technique, how to extract anything. For example, just mean density of this point in the complex plane. And partly my goal of this talk is just to show that some progress is possible. But before doing that, I'd like to remind about another important feature of non-self-adjoint operators. Non-self-adjoint operators generically are also so-called not normal. They do not commute with their adjoint. And therefore, each complex eigenvalue corresponds to two sets of eigenvalues, so-called left eigenvalues and right eigenvalues, which correspond to two related eigenproblems. So right is this, and left can be looked at as right for a joint. So this is a definition of left and right. And then important role in applications. In fact, this non-normality was long recognized to have important effect on stability of eigenvalues with respect to perturbations of the matrix entries of various types, and plays very important role in numerical analysis related to these types of matrices. And in particular, a very important object is so-called eigenvalue condition number, which can be shown to be a very important measure of sensitivity of matrix to perturbation. And this is basically the following object. For a given eigenvalue, we take left and right eigenvectors, we form corresponding scalar products, and between left, between right, and then left, right, right, left. And this ratio by Cauchy-Schwarz, it's easy to see that it's always larger or equal than 1, and one can show that it's 1 only if matrix is normal. So deviation of this from 1 is exactly characterization of non-normality, one possible way of characterizing non-normality of matrix. So interest in condition numbers of various ensembles of random matrices started more than 20 years ago from important paper by Choker and Merritt in physical literature, who showed their relevance for some dynamical systems. But essential progress happened, in fact, only recently, where first by Bourgade and Dubash, and then in a series of further papers, it was realized that one can calculate for classical ensembles of non-self-adjoint matrices known as Genibra ensembles, one can calculate basically statistical properties, the whole probability distributions of these objects. As Choker and Merritt were able only to calculate mean value of this condition number, but now, recently there was a progress in understanding the whole distribution, and it turned out that this is a heavy-tailed variable where all moments beyond mean, in fact, diverge. That's why Choker and Merritt were not able to calculate higher moments. So, one of the goals of this work will be to also to shed light on non-normality properties of this. In fact, simultaneously we're studying correlation or densities in the complex. So, what is appropriate, in fact, framework for doing this? In fact, it's known in the mathematical literature and in different language and physical literature that when we deform and make our matrix non-self-adjoint, there is a corresponding important spectral object called Lipschitz characteristic function, which is a function depending on, in general, complex parameter lambda, such that when lambda is real, this is unimodular function. So explicitly, it's constructed in the following way. Is just product over all eigenvalues of this parameter lambda minus conjugate eigenvalues in the numerator and lambda minus zi in the denominator. So we see that ZI's eigenvalues of non-self-adjoint matrix play the role of poles of this matrix in the complex plane, and their images play the role of zeros of this matrix. It's not obvious, but matrix algebra shows that the same object can be written also explicitly in terms of a resolvent of the corresponding non-self-adjoint matrix. Namely, one takes the resolvent and takes element 1, 1. So projection on this E, I remind you, E is just vector 1 and then 0. Projection on this vector, they multiply with gamma. This construction in terms of the resolvent, one can show that this is exactly this. It's not obvious, but go into eigenbasis of this non-self-adjoint operator, one can prove and check it. So the same function in physics literature is called scattering matrix, because it's indeed one can give meaning to it as some matrix describing how waves sent on the system and reflected are related to each other. But it's important that basically, I just reiterate that important for us that poles are resonances. Now, what are residues? Of course, it's very easy to read off residue from the left-hand side, just in terms of this complex conjugate eigenvalues. But if one does the same from the right, one gets a very useful identity, which we identified with Melik about 20 years ago, that in this case, condition numbers can be written explicitly in terms of eigenvalues and their complex conjugates. This is a very special feature of a perturbation being rank 1. If we consider more general perturbations, which is also meaningful in scattering theory, this will be lost. But this case is special, and therefore there is a relation. If we know the joint probability density of all Z, we can hope to get some information about statistics of this non-orthogonality factor. So in order to characterize these factors, we just introduce their negative moments sampled around a given point in the complex plane. So we just take these O's, we raise them to negative powers, negative because we expect that probability distribution has heavy tail, so positive will be divergent. So negative is a natural, but otherwise it can be anything, not integer, just anything. And we weigh them with delta functions, spectral delta functions, just to discuss only those eigenvectors which correspond to eigenvalues close to a given point in the complex. And we are interested in this moment, so we calculate expectation with respect to joint probability density of all Z. So after some manipulations, it turns out that when n tends to infinity, one can show that these moments can be expressed in terms of characteristic polynomial or ratio of products of characteristic polynomials for non-self-adjoint matrices, for these matrices. Unfortunately, so far there is no any regular tool which allows us to evaluate this type of object. So this is, I believe, useful representation, but we are not able to deal with it directly. So to develop some attack on this object, we decided to use, it's useful to exploit the rank one nature of the perturbation, and determinant of rank 1 perturbation of any operator can be very easily related to basically element 1, 1 of the resolvent or projection of green function. And then this can be written in terms of eigenvalues, obviously go into eigenbasis of unperturbed, of Hermitian operator. So we know about that, but also, fortunately, there is in the literature the knowledge about statistics of the residues in this particular object, which are just nothing else as squared projections, just first components of corresponding eigenvectors squared. And those are known to be independent on eigenvalues, which is very important and helpful, and being distributed according to this probability distribution. So we know explicitly the joint probability density of all WIs, all residues, and they're independent on denominators. So one can use this, especially effectively in the large n limit. This constraint is not very important, and in fact not operative, and they behave like independent, basically random numbers, and then it's easy to calculate some statistical properties or generating functions for G. One can then reduce basically this calculation of this object in case of rank 1 perturbation to joint statistics of these objects, these resolvents, and corresponding characteristic polynomials. It turned out that if one does this calculation, one finds that in order to calculate for any beta these moments that we introduced, one needs to know now specific correlation functions or involving ratios of the product of characteristic polynomials of self-adjoint these three diagonal beta ensembles of Dmitriev and Endelman. So namely, one needs to know expected value, or in the numerator we have modulus of characteristic polynomial at some point slightly shifted to the complex plane in power 2 beta, and in denominator product of two characteristic polynomials in 2 points with a distance comparable with delta. Thank you. And we need to evaluate this. For beta equal 2, we will deal with integer powers here, and this is this calculation. I mean, this object, asymptotical, this object is known from our paper with Strachov. And for beta equal 4, we also have here only integer powers, and this can be extracted from Borodin-Strachov from this type of general object, which are very, I believe, very important in business of zeta function, in fact. But for beta equal 1, we deal here with square roots, with half integer powers. Fortunately, with André Nock 2 years ago, we were able to evaluate a few cases just using supersymmetry approach advocated by Tom yesterday, and by some miracle, I believe, it's exactly the object which appears here. So we were able also to evaluate it for beta equal 1. So I won't dwell here too long, because we have here, but basically for classical values of beta equal 1, 2, and 4, one can calculate not only the moments, but restore the whole probability density of these non-orthogonality factors in very explicit form. I hope that if we know it for 1 to 4, we could conjecture it for any beta, but unfortunately, it's all expressed in terms of differential operator, which is obtained in number of terms summing from 0 to beta. So since in this form is not very helpful for guessing what happens for non-integer or in not even irrational, say beta. So this was a bit of disappointment, because I hope to put forward a nice conjecture on any beta. But so we continued. Again, I need to accelerate a little bit and just consider what happens if parameter gamma is very small. We just slightly perturb our eigenvalues to the complex plane. Then one can use what is known as perturbation theory and characterize the motion of eigenvalues to the complex plane by just combinations which involve again these WIs and eigenvalues of unperturbed problem, and also similarly for non-orthogonality factors. So we can characterize both complex eigenvalues and non-orthogonality factors in terms of some sums. And then we can perform again averaging over these Coulomb gases. And then we came to objects which we were able to calculate exactly for 1 to 4, but in the form which allows to conjecture for any beta, because beta enters as benign parameter. So I claim, I just put forward, together with Rachel Tublin, we still unpublished, it's under preparation, that the following expectation, some combinations involving non-trivial powers of characteristic polynomials and ratios of them can be evaluated explicitly, and for any beta conjecture to be given in terms of Bessel-Macdonald function. Something maybe not unlike this formula involving standard Bessel function that we've seen for pair correlation function. So it's here Macdonald function. In fact, object which is very close to what I've already shown to you for non-self-adjoint matrices, we can evaluate in self-adjoint case, again for 1, 2, 4 rigorously, but it's presented in a form involving integral of Bessel-Macdonald function. Again, beta enters as a parameter, so one can hope that this is a good candidate for conjecture being valid for any beta. Okay, I won't discuss what follows from this non-orthogonality factor. One can extract information about these non-orthogonality factors using these conjectures, check it numerically. So my conclusions are the following. Rank 1 non-Hermitian deformations of beta-Hermite ensembles are rich and largely for beta not equal to 2 unexplored objects, deserving further studies. Results for beta 1, 4 hint towards some hidden integrability, and probably there is some regular techniques like something related maybe to orthogonal polynomials not yet discovered, which allows to calculate things explicitly. Evaluating closed form local scaling limit involves products and ratios of powers of characteristic polynomials for beta remains a considerable challenge. Intriguing objects especially involve these powers, determine characteristic polynomials to powers beta over 2. We attempted to conjecture explicit form for some particular combinations. There is a hint to hidden structure probably in sine beta process because of explicit formulas. And now I pose the challenge for the audience. Is it possible to construct a single parameter deformation of the Riemann zeta function, which in a controlled way, I will explain what I mean in a controlled way, removes all zeros away from the critical axis? By controlled way, I mean something of the sort that we did here. There is a parameter gamma. When parameter gamma is 0, they are all on the real axis. But when I change gamma, they go to the complex plane just somewhat. Okay. Indeed, but I think that it may be, you see, sometimes you cannot solve a difficult problem, but you can deform it and it gives you some nuance. I think it would be interesting to have or conjecture some deformation which moves it in controlled way, not like, for example, counterexample, I mean, bad example of deformation will be Hurwitz function, because it has, of course, a parameter in it, but whatever smaller the parameter, one can check or one can find in the literature that in the whole critical strip between 0 and 1 immediately becomes filled in with zeros, with complex zeros. So it's not controlled in my way. I cannot use small parameter, just slightly shifted to the distance comparable with separation along the critical line. So this is, I think, a problem which I personally would be interested to know the answer. Thank you very much for your attention.
So, questions, comments, thoughts?
Some beta ensembles that are tridiagonal or diagonal. Are there any belief about if there exists any kind of beta ensembles of unbounded rank?
Sorry, last bit. I missed the last bit.
Beta ensembles with unbounded rank.
This is interesting question, which I don't think that anyone addressed. You mean some say further banded or of the sort with some. A very interesting question. In fact, construction is a bit rigid here, but I think that there should be some universality also in this. So it's a very valid question, and would be very interesting to understand whether there are other types of matrices which are in the limit or exactly. You see, here, of course, important that even for finite n, it's exactly Dyson gas. This is an impressive thing. But I could imagine that there should be universality class where other types of matrices possess similar asymptotic behavior, but it's completely open and nothing is known about it.
So sometimes, statistical mechanics, when you introduce the parameters, they allows you to differentiate whatever, and then learn something about the system when the parameter is 0. So do you have something like that here in the sense that you know how to compute for gamma, then you can.
You see, okay, maybe there are other ways, and probably there are other ways, but this perturbation theory in gamma gave rise to correlation functions of characteristic polynomials, which we were able to conjecture. So this allowed us to introduce structures which eventually for 1 to 4 were amenable. Otherwise, you do not know where to look at. But these structures naturally came from perturbation in that gamma. So, in fact, this logic was followed.
Any further questions or thoughts, speculations? Right. I mean, it's striking that the answer that you conjecture for the ratios of characteristic polynomials solves a differential equation, which is the general case. That usually that's the case. So can one see that this must be always the case? That you get some integrable ODE?
Okay, we know systems of ODEs which correlation functions of characteristic polynomials for classical beta satisfy, but someone was not much. All information which I know about correlation functions was not obtained in this way, although they are known to satisfy this system. I think it's not much explored way, but maybe this is just an alternative angle of looking at that, and eventually one may prove something like this. But this hypergeometric function that you know and been used, I think suggests that there will be some differential systems behind it.
Right, if there are no further questions or thoughts, let's thank Jan again.